I'm going to, I think if my charge, I'm not really a galaxy feedback person, but I think my charge here was to tell you a bit about accretion theory as it applies to active galactic nuclei, and maybe give some sort of connections to feedback and galaxy evolution. There'll be another review talk tomorrow on more explicitly on feedback itself. So let's see. Okay, great. Oh, and I should say, of course, this is a huge topic, so I'm giving my own biased sort of a little bit focus of what I think is interesting and important. One thing I don't have a lot of time to talk about is jets and radio mode feedback. I do want to advertise this review article. This is not going to, laser pointer's not going to work. This review article I wrote with Sasha Chukovskoy, and we talk more about jets and radio mode in there. All right, so I just have this sort of very quick, just a few points on, so the whole theory of accretion is now over 50 years old, which seems crazy to me, going back to Shakuri Sunyaev and actually even others before that paper. And so it's kind of amazing how little progress we've made in some ways. It's kind of sad, but I won't be melancholy. I would say, though, the main things we've learned since then is that magnetic fields play a very important dynamical role. They probably transport angular momentum. They are probably what's responsible for launching jets. And they probably are actually important for supporting the disk, we think now, and potentially preventing instabilities and things like that. So this has actually led to a fairly strong reliance on numerical simulations for theoretical progress, because to model magnetic fields, you typically do really need to simulate them in 3 dimensions. And that's what makes this a hard problem for, I think, further advancement. At the same time, the observers have been trying to sort of approach this problem from the other end and sort of give us models to work with. That's had mixed success, I would say. But I'd say the big main success that everyone's probably already aware of is this sort of unified model. And so what they basically have discovered is that most AGN, or many AGN, are intrinsically the same objects, but depending on where we're viewing them from, we see one thing or the other. And so the main thing is that we have this torus. We don't this sort of obscuring torus that if you're looking edge on, you miss the inner accretion disk, you miss these broadline region clouds that are providing us particular emission lines. But if you sort of are looking down this way, you can see into the inner disk, and you can see these broadline clouds and stuff. Okay. The problem is, from a theoretical point of view, we have ideas. I don't want to say there's no ideas here, but we really don't have a consensus for what's producing this torus. We don't have a consensus for why they're broadline and narrowline clouds here. And actually, as I'll point out, I don't even think we understand the accretion disk all that well. So there's a lot to be done. Now, for accretion, of course, many people who work on accretion don't just work on active galactic nuclei. And it's important to keep that in mind, okay? We can learn a lot by looking at other systems like X-ray binaries, which are nice. They're very bright. They vary on shorter timescales. You learn a lot from that. The really important question is how much of what you learn there carries over to active galactic nuclei, okay? And I'm not sure it all does. So we have to be careful about those interpretations, both observationally and theoretically. Another area is that we're very interested in quasars. I'm mostly focused on quasars and very luminous AGN in this talk. But of course, we also can study low luminosity AGN. Both are probably important for feedback, of course. The nice thing about low luminosity AGN is that in 2 sources, M87, Sag star, we can actually image them. And now we're getting very interesting constraints from those particular sources. Again, the question is, what carries over to luminous AGN and vice versa, okay? So I'm gonna give a quick review of accretion disk theory, some of the important points. This is gonna be very fast. I'm sorry if it's too fast. One thing you've probably all seen at some point or another, we have this standard model of accretion disks. It only requires assuming conservation of angular momentum and energy, and a boundary condition at the inner edge of the disk. That boundary condition is usually assumed to depend on details of the black hole spacetime, the location of the innermost stable circular orbit, things like that. If you ignore some of the details, you basically find an equation like the one up there. And what this tells you is that the temperature of the emission, as long as all the energy released is radiated locally, goes as the inverse of the mass to the -1/4 power. More massive things are cooler. It depends, of course, on the accretion rate and the radius. Now, you can generate a spectrum from this just using black body thermal emission. You just break the disk up into rings, add up the black bodies, and you get this multi-temperature black body, whose peak is basically determined by the temperature of the hottest innermost annulus. And so if this was all there was to accretion disk theory, basically supermassive black holes would just be cooler versions of X-ray binaries. And that kind of works to first order, right? X-ray binaries are in the X-rays, black holes peak in the UV. The agreement breaks down if you look more closely, though, as we'll talk about. Okay, and then so this tells us, I think there's 3 pieces of physics we really need to understand very well in order to understand AGN. The first, as I've already pointed out, this inner boundary depends on the space-time of the black hole. The emission depends on what's on the space-time of the black hole. We need general relativity in our models to account for that. The other thing, so Shakur and Sunyaev, one of their really important contributions is they gave us a model for the stresses that transport angular momentum in accretion disk, this famous alpha disk prescription where the stress is some constant alpha times the total gas plus radiation pressure. And if you take that model through, what you find is these luminous accretion disks are all basically radiation pressure dominated. Radiation is what's supporting the disk. Hence, radiation forces need to be modeled very well in these systems, okay? And then finally, Balbus and Hawley showed that MHD turbulence driven by the magnetorotational instability can yield the sort of high alphas, the high accretion rates that are observed in these systems. That tells us we need magnetic fields. We need at least these 3 physics inputs to have a good model, okay? Now, the other thing I just want to review quickly is timescales. Basically, if we're just talking about thin disks, we only have 3 important timescales in accretion flows: a dynamical time, which is just essentially the orbital timescale; a thermal timescale, which tells us how quickly these disks can cool; and an inflow or viscous timescale that tells you how quickly stuff moves through the accretion disk. The hierarchy is such that the dynamical timescales are days, probably in AGN. Of course, it depends significantly on the mass we're talking about. Millions to billions solar mass black holes will have different timescales. Thermal timescales can be weeks to months, and inflow times can be decades, even centuries for some of the most massive systems. Observations tell us that alpha is somewhere in the ballpark of 1/100th to maybe even 1 in some cases, depending on where you look in the disk. So thermal timescales are usually about that factor, longer than dynamical timescales in this model. All right. Okay, that was quick. I hope that was mostly review for most of you. Now I want to get into what observations tell us about these theoretical models, okay? I'm starting by a comparison of AGN X-ray and X-ray binaries spectra, okay? The plot on the left is an X-ray binary, LMCX3. It's my favorite X-ray binary. You can ask me why. But this is a fit from work I did as my PhD thesis. The orange curve there is a model of a Shakura-Sunyaev relativistic accretion disk fit to a disk-dominated state of this X-ray binary. There is some absorption included that accounts for the drop-off at about 0.3 keV. When you do that, it fits wonderfully. And it doesn't just fit this one single snapshot, it actually fits the source as it varies its accretion rate, okay? So this model really works well in X-ray binaries as long as you select a subset of X-ray binaries. The plot on the right, which might be a little harder to see, is similar models fit to AGN quasars. What we've done is we've taken the mass estimates and we've varied the accretion rate so they match in the optical. And what you see in all 3 cases, and this is quite general, I haven't cherry-picked these, the models actually extend into the extreme ultraviolet, where the spectra basically all turn over around 1,000 angstroms. This is very hard to understand because those temperature scaling I just showed you says that more massive things should peak at lower wavelengths and less less massive things should peak at longer wavelengths. They all peak around 1,000. Okay, we don't see this evidence for this mass dependence from the model. And this is a real problem because it looks like 70% or more in some cases, the accretion luminosity is just not coming out. Okay, now there are caveats to this. There's dust that might not be modeled in the host galaxy. But again, if we're talking about type 1 AGN, we're looking down, a relatively open, region. It's not clear there should be enough dust to be getting rid of this. And there are other indications that this is really missing. Okay, so I would say we have a real problem just in the spectrum. There's another famous problem, which is size discrepancies. In some of these systems, particularly in the lens quasars, we can use microlensing variability due to the stars in the lensing galaxy. Basically, depending on the size of the Einstein ring of the stars to the actual size of the accretion disk in the quasar, the variability, if you're small or large compared to the Einstein ring, you get different variability that allows them to constrain the size of the emitting region. And they generically find that it's by a factor of 3 too big, in some cases a factor of 10, bigger than the Shur-Kuros-Sunyaev prediction. Similar constraints come from using the continuum reverberation mapping method. Those are a little harder to interpret, but they give you the same point in the same direction. And Amy Secunda is going to give us a talk on that, so hopefully she'll say more about that. I don't have time. All right. Now, the last thing that I just want to highlight is this extreme variability. In AGN, we have these cases of the changing look AGN that are varying on timescales of months to years. This is shown in this plot at the right. So this is BOSS spectra and SDS spectra. I think these are maybe many years apart. I forget the exact numbers, but you can see the continuum. One is shown in red, one is shown in black. They're changing significantly, and the lines are changing also as a result. But I just told you these should only be, if this is only varying on the inflow time, it should be decades at most, okay? So this only works if we have variations on thermal timescales or some other weird thing like TDEs or binaries or doing interesting things in the disk. Understanding this, I think, is a challenge for standard accretion disk theory. I probably have too much in here, so I'll just go over this slide really quickly. I just want to remind people, we do have mass estimates for a large sample of AGN. These are SDS quasars. This is Yue Shen's work. It's pretty old now, but it's still very relevant. So this is mass versus bolometric luminosity. And don't worry about what's going on at the high end, but if we just focus, because we're probably missing a ton of stuff down there. But right here, we have very, very few sources emitting at the Eddington luminosity or above. Okay, and so I think that's a really important question: is why is that? Is it because of how they're fed, which hopefully you all will figure out, or is there something going on in the disk as the material accretes down to the inner regions that's limiting you to be less than the Eddington luminosity? And it's not obvious why it should be characteristically 1/3 of the Eddington luminosity. I think that's an important question. All right. The last thing that the observations are telling us is that, and I don't have a lot of time to explain this in detail, but they're telling us that strong magnetic fields are present close to the horizon of black holes. Okay. We already kind of had hints of this by trying to explain the powerful jets that are observed in radioloud quasars. But if you look at Sagittarius star and M87, both show evidence in the modeling of strong magnetic fields. I think the best constraints come from the M87 polarization results, where they need basically Faraday rotation internal to the source to explain the observed polarization. That's a very strong hint that strong magnetic fields are present. How they get there and what they do to the accretion flow is, I think, a very important problem. Okay, so I hope I'm doing on time.
13 minutes.
13 minutes. Oh, better than I thought. Okay. So that's the 20 minutes, right?
Out of the 20. Yeah.
Okay. Great. All right. So I guess I kind of want to get into what I think. Okay. So just to be clear, what I'm saying is accretion disk theory. There's two different messages there. There's some very interesting things that we need to explain, how we have these magnetic fluxes, why the Eddington ratios are only 1/3. And they're rarely above that. But at the same time, I'm telling you that accretion theory, or at least standard accretion theory, does not apply very well to AGN. There's some real problems here. Okay? And so I want to frame this as why, and so I'm saying that accretion theory works pretty well in X-ray binaries, not perfect, but I think it works much better, okay? So I think there's a good question, a good way of framing this question is what is different about AGN that matters for understanding accretion in these sources, okay? All right, and so one important thing is environment, okay? Basically, you know, in binaries, there's just the other star nearby for the most part. But in AGN, you have a central star cluster. There could be objects embedded in the disk. There's all sorts of interesting things going on in the vicinity of the accretion disk that might be changing things. And I think it's very important to understand this, what's going on in the host galaxy, of course, to understand what's going on in the, help understand what's going on in the accretion flow. It's not just, we need to know the accretion flows to understand feedback. We need to know galaxy evolution to understand accretion. Mass supply, this is obvious, right? In an X-ray binary, you're just getting stuff right from the companion star, either a wind or Roche lobe overflow. But in AGN, they're fed by, I don't know. This is why I'm here. I want you guys to tell me, you all to tell me how they're being fed. I'm very excited. There's appear to be a lot of talks on this. There's probably more than I listed there. I hope that you're all going to give me a clear, consistent picture of this. I hope, but we'll see. Okay. Now, accretion regime is important. I think AGN are much more radiation pressure dominated than X-ray binaries. X-ray binaries are probably radiation dominated too, so it's not such a clear-cut distinction, but AGN are radiation pressure dominated by factors of 1,000 or more in the standard model. And of course, that suggests, I don't have time to talk about this, but that actually comes with a famous instabilities in the Shakura-Sunyaev model. And those may be having an impact. And then I think this is something I'll say a bit more about. One thing that's very important is electron scattering dominates the opacity in X-ray binaries, but atomic opacities are much, much more important in AGN. We're in the same temperature and density regimes as massive stars. And as we know, in massive stars, opacities have a huge effect. It's probably true in AGN as well. Okay, this is a slide. It's maybe a little hard to read, so but this is trying to demonstrate that. So, all right, so on the left, we have, so these are basically mean opacities. There's two types of mean opacities plotted here. On the left is the Planck mean. You just get this by integrating the opacity against a Planck spectrum. On the right is a Roslin mean. You probably remember this from some radiative transfer course. The Roslin mean basically tells you what the radiation flux is doing in the diffusion limit, okay? So it's sort of integrated against the radiation flux. And so okay. And so, anyway, so the key here is that the values are way, way above electron scattering opacity once you get down to lower temperatures. And the dash curves here are Kramer's laws for free opacity. This is what's usually used in models. And you can see the Planck values are way, way above what is assumed in the free values by factors of 100 to 1,000 in some cases. This is really going to be important. All right. So I just want to quick talk about simulations because this is the dominant way we study these systems. We need to solve the fluid equations, conservation of mass, momentum, and energy, coupled to radiation forces, and net heating and cooling. We like to couple this to a solution of the radiation transfer equation. Other people use other methods, M1, flux limit diffusion. We solve the angle-dependent transfer equations. This is actually work by Yanfei, who just arrived in the audience here at the CCA. And so this allows us to model the radiation very well. Recently, working with Chris White, also here at the CCA, and Patrick Mullen at Los Alamos, we've extended this to general relativity. So we can do these simulations in general relativistic spacetimes with full transfer. So I just want to highlight a couple recent results with the little time I have left. These are global simulations performed by Yanfei and Omer Blaze. And what the key here is they're done for 10 to the 8 solar mass black holes. So they're done for AGN, and they're done using these opal opacities I just showed you. And the disk structure is very different from an accretion disk, Shakura-Sunyaev disk. There's lots of convection going on. The disk is much thicker. It's varying on significantly on shorter thermal timescales, not just on inflow timescales. I think including these sorts of opacities is very important. A lot of the simulations that are done for accretion are done for X-ray binaries. It's very important that we actually simulate AGN if we want to understand AGN. Okay, this is some work done by my postdoc, but as well as others. One thing that's very important is AGN show these broad absorption line outflows. This is blue shifted absorption at 10 to maybe 30,000 kilometers per second, so up to about 1/10 of the speed of light. These are seen in a fraction, I think something like 20%, 15% of sources, but it's possible that's just a viewing inclination effect, that we only see it in some sources. Daniel Proga and now Sergei Daida have simulated this in 2D. Daniel did this, Sergei did this with Athena++ for, this is a simulation of his. The left shows the density with velocity and the right shows the X-ray intensity. The key is that you have to model the X-rays to get the ionization structure right. But even when you do include the X-rays, which can ionize the atoms and otherwise ruin the opacity, you still get very strong radiation forces, enough to drive very strong outflows consistent with broad absorption line quasars. The key thing is that the most important thing for this audience, the outflow rates he's getting are comparable to the assumed inflow rate, which is about 1/3 of Eddington. So generically, I would say that these accretion disks are probably driving outflows with kinetic energies that are comparable to what you might get from the Eddington limit arguments, 10 to the 44 for a 10 to the 8 solar mass black hole, possibly all of them that are at high Eddington rates. Okay, I think I'm out of time. I just want to show you, that's a 2D simulation. We really want to do fully coupled 3D simulations. I think we're close to it. We have time. This is my collaborators. We have time now with exascale computing. We can do simulations on Frontier. This is using Athena K. This is a simulation by Chris White. Yanfei is doing simulations with AGN. And this really shows the power. These are doing full transfer. This is 48 angles in this case at very, very high resolution. And so soon we'll be able to do this, or we're already doing this for AGN. And I think ideally we'll be doing fully coupled with the right radiation opacities included very, very soon. Okay. And so I'm sorry, I think I went a little bit over. I'll stop. I'll just summarize. I'll say real quickly, I think the main things that are important for this audience is it's very important to understand how we feed accretion flows, to understand accretion flows themselves better. Really, I think it's important to understand how magnetic fields are brought in and what the field geometry and accretion disks are. I think we'll hear a lot about that. And then I think what is interesting is we should really be thinking about how prevalent these outflows are in AGN and whether they and how they impact feedback in galaxies. And I'll stop there. Sorry, I went a little over.
All right, are there any questions for Shane? I'll just run around, I guess.
Thanks for a very nice talk. So I remember speaking to Jim Stone about the opacities a few years ago, and him saying basically they're very, very uncertain. So is that still the situation, or how well do we know these opacities, since you've made the argument that this is a really essential ingredient?
Yeah, this is a great question, and I'm glad you asked it, because I would have liked to say more about this.
Good.
So the opacities, here's what the first thing I'll say, because I went over this a little too quickly. So these opacities are very well determined in the sense that, you know, these are opal. They're, you know, the mean opacities are pretty well understood. We know most of the transitions that are relevant. We're probably missing a few, but you know, this is pretty well measured. Now, the problem is that these really only apply when you're optically thick. Okay, and yet we're using them even when you're optically thin. So this is really, I think, the uncertainty that Jim is talking about. Now, when we go to Sergei and Daniel Proga, the work that they're doing, they're not using mean opacities. They're using this force multiplier formalism that was developed for massive star winds. And so in that formalism, you're basically assuming the radiation field is optically thin, and then you're basically relying on calculations that include tens of thousands, hundreds of thousands of lines in this optically thin limit, and getting the radiation force from that. Okay, and that can be 1,000 times bigger than the electron scattering opacity. That's why I think we drive these strong winds from AGN generically. Now, the problem is whether those lines are there or not depends on the ionization state. And because of these strong X-ray force, the X-ray components, we can ionize it away. So that's why that's what Sergey's trying to do. So that's why I think we need these fully coupled simulations. And so what we need is a prescription that goes from the diffusion limit, mean opacities, to this force multiplier. We're never going to be able to do 100,000 line calculation with hundreds of thousands of lines, but I think we can use the formalism from the massive stars to sort of make a transition, and that's probably what we'll do. And I think that's reasonably robust.
Great, thank you so much.
Other questions? Shane?
Thank you. Really nice and comprehensive talk, so I really appreciate it. So my question is on what you suggested about the environment affecting how black holes are feeding. So for instance, you mentioned star clusters. So my question basically is, how can things, very generically, things happening at, say, a million Schwarzschild radii affect what happens, on accretion disks on smaller scales. So what type of effects are you thinking exactly?
Well, so the question really is, yeah, I agree. If it's really a million, then it probably doesn't matter that much. But I think the question is, at thousands of gravitational radii, do we actually, are we impacting the accretion flow in an interesting way? And I would still say maybe even at 100,000 or a million, you do worry, okay, so I presented this thing that I said that, these are not accreting at above the Eddington rate. And maybe I should have said a little bit more about that. So, the question to my mind, sorry, is basically, is there outflow continuously in these disks all the way from millions of RG all the way down to hundreds of RG? Is that what's giving us in the end something, of course, the Eddington limit? It's a little bit of a coincidence, because those opacities that would be driving outflows or doing things probably don't care about electron scattering. But I think if you have things embedded in the disk, if you have things interacting with the stars, even at fairly large radii, they may actually be, stirring things up. They may be undergoing supernova. They may be, helping to drive, outflows by injecting energy. I think the other thing that could happen is if they can deliver mass closer to the black hole, either through stars with winds and things like that. It's just another channel for bringing material in. But I think the real question is, if stuff is embedded in the disk, how far does it get in before,
May I ask a quick follow-up? So I was thinking also of instruments such as gravity, and especially Gravity Plus in the future, that in principle should be able to map part of the accretion disk. Do you think that will, I'm not an observer, but this has been very exciting hearing about it. Do you think that this is really deliver what is promised?
Yeah, so I'm very interested in the gravity results as well, for the same reason. I mean, so I think the problem we have, one of the big problems, and this is a problem for all of you really, is that we don't really understand accretion flows on parsec scales, right? And so I think trying to look at nearby systems with things like instruments like gravity and trying to get a better handle with interferometers and stuff of what's going on in those scales is actually, I think, very important for understanding how these things are fed. And hopefully in at least some of these nearby systems, even going down to horizon scales. I think, unfortunately, you can only do that in the lower luminosity AGN, which is still very interesting. I don't know if they'll tell how much gravity will tell us about the more luminous phase of, more luminous AGN, except at maybe larger scales.
Let's thank Shane again.
In the this one, on the desktop. Yep. Right, should we get started? Okay. Thanks a lot. So thanks to Sophie and Doug, especially for bringing us here. I'm super excited about this week. So my name is Daniel Angles Alcázar. I am at the University of Connecticut, and today I'm going to tell you about some recent progress on multi-scale simulations of black hole accretion and feedback. So I'm going to be focusing mostly on the fueling aspect of this from the galaxy formation point of view, and then going down to as close as possible to the black hole as we can. Hopefully at the end, I'll get to advertise some of the work on feedback as well. So from the point of view of galaxies, this is what we want. We want to be able to model a large volume of the universe. You see the beautiful cosmic wave in the background, dominated by dark matter, and then galaxies forming at the center. We want to understand, the complex multi-phase properties of gas in the interstellar medium, how stars form, how stellar feedback affects things, and then how black holes grow at the center and affect the galaxies and the large scale structures. So lots of physics coupled over many, many scales. And we want to do all of this at once, which is obviously very, very challenging. So if we want to get the large scales right, we need large volume cosmological hydrodynamic simulations. In this case, we are obviously limited by resolution. So think of modeling, implementing black hole growth and feedback with a resolution of about 1 kiloparsec. So lots of subgrid physics, lots of parameters that we need to tune in order to match observations. And so many of the predictions in terms of, for example, black hole properties, impact of feedback, and galaxy evolution will depend on how we parameterize these models. And I'm just here highlighting some of Melanie's amazing work comparing many of these Cosmos hydro simulations, and then which aspects of black holes and AGN are consistent between them, and many others are not as consistent. If we want to get more details, we need cosmological zooming simulations where we focus all of our resources into a single galaxy or group of galaxies. And so this is just showing one example from the FIRE simulations. There are many other teams working on high resolution zooming simulations like this, where now you begin to resolve the actual multi-phase structure of ISM, how stellar feedback affects black holes. And for example, here in the middle panel, you see that black hole mass versus galaxy mass, black hole masses are really suppressed by stellar feedback at early times. And then you have to wait until the galaxy stabilizes, stellar feedback becomes less efficient, and then black holes begin to grow and converge onto the scaling relation. So these are things, physical processes that are totally missed in lower resolution large volume simulations. But now here, the physics of black holes is modeled on a scales. Think of something between tens of parsecs or 100 parsecs. So again, much better than what we can achieve with large volume simulations, but it's still pretty much, we still depend on subgrid models for this. So if we want to get closer and closer to the black hole, then we need to start with zooming simulations, and then refine, increase the resolution as much as we can. So this is what we do in these simulations, which we call cosmological hyper-refinement simulations. We start from a standard FIRE simulation, and then we let the code evolve, and then increase the resolution in the gas component dynamically. So the gas, the closer it gets with split particles, this is a Lagrangian code in Gizmo. And so we go all the way to modeling explicitly the inflow rate down to subparsec scale. So that's the black hole over there interacting with the potential dominated by the stars. And so with this technique, now we can go to a mass resolution of just say for the 10 or 20 solar masses per particle, and measure explicitly the inflow rate down to subparsec scales. So here in the next slide, this is another view of the same type of simulation. So in this case, showing Mach 3-color images going from a couple of megaparsec scale in the top left, and then all the way down to the central 20 parsecs. And so really complex, very complex dynamics at the center of this galaxy. There is a sort of merger going on larger scales. You can see galaxies at about like 20 or 30 kiloparsecs away. And so what I wanted to emphasize also is that it's not just about resolution. So many codes can refine and refine to higher resolution, but it's also very important to include the a huge range of physics that happens at different scales and have models that can work with a range of different resolutions. So this is just a list of things that we incorporated to make these models happen. For example, you need models that can that can model star formation and stellar feedback across the gradient of resolution that we have in these simulations. Very important to have adaptive gravitational softening and many other technical details for to capture the whole dynamic range. So on the left here, you see the nuclear gas surface density distribution for a standard fire simulation of a massive galaxy. These are the central 100 parsecs. And this is already pretty good. We see some structure, but then on the right, you can see what happens when we hyper refine, lots of more details that we can look at. So now let's look at here the accretion history of a black hole. So this is the accretion rate versus cosmic time for a massive galaxy going down to redshift 1. Accretion history, this is here modeled at a subgrid level. And what we can do now is we can zoom into a few specific phases to then hyper refine and measure explicitly what is the inflow rate on subparsec scales. So here we are zooming on when the galaxy had really the densest nuclear densities at the center. And in fact, we found that those conditions are very good. They're really powering a quasar. Like accretion. So here we have accretion rates of a few solar masses per year sustained. You see in the linear animation there, the black hole really moving around, interacting with a very dense non-axis symmetric stellar disk in the inner few parsecs. But then if we go back in time only 40 million years, the conditions totally change. So in this case, the gas is much more turbulent. The densities at the center are not as strong, and this is driving accretion rate that can vary over 4 orders of magnitude in only a million years. So the top left panel here is showing the accretion rate explicitly on subparsec scales. And then we can see peaks of accretion rate up to 10 solar masses per year, but then sometimes going down to much lower accretion rates. So totally different conditions compared to the full quasar phase. And finally, the same galaxy, but at later times, much lower gas surface density. So this is near redshift 1. We see the formation of a central cavity due to consumption by star formation, stellar feedback, possibly an inner limb resonance. And so the black hole can only grow when there is some gas destabilized from the edge of the cavity and torqued by the stars. And then we have a short period of accretion, with accretion rates of order 0.01 solar masses per year or so, but again, totally different conditions. And so basically we were able to run these experiments for 3 different conditions. The 3 of them were basically a big surprise, the type of accretion histories that we got, and it's really motivation to keep doing more of these hyper refinement simulations. So many interesting results. I don't think I have the time to cover this in a lot of detail, but we find that gravitational torques from non-axis symmetric stellar structures dominate angular momentum transport basically across the entire range of scales, down to what we can measure here. So it's normally the case that it's the stars near the gas on the same scale that is dominating the torques, but sometimes there is very interesting coupling of scales. So in conditions when there is a huge non-axis symmetry on kiloparsec scales, sometimes that can be impacting the dynamics on parsec scales. So very important to try to cover all of these scales together. Then in terms of the star formation rate AGN connection, as previous work, we find that there is a good correlation between nuclear star formation rate and the accretion rate, but then the time scale of accretion changes so quickly that this time variability decouples AGN and star formation. And then some very interesting implications, for example, for in the end for the coevolution of black holes and galaxies, which may explain by basically a common gas supply driven by regulated by gravitational torques. And then we can also study the gas angular momentum across the scales. These simulations naturally produce misaligned like parsec scale disks compared to the larger scale galaxy. Now, if we want to go to even higher resolution and begin to see the disk, we need to do many things. We need to increase resolution, but now we need to start forming individual stars. So in the previous simulations, we went down to mass resolution of about 10 solar masses. in order to keep zooming in, we need to switch to a model that can handle forming single stars, like really stars one by one. And this is what we have done now in a series of papers led by Phil Hopkins, the Forge in Fire papers. So here we are zooming in from megaparsec scales all the way to 100 Schwarzschild radii. And so this is really trying to combine sort of the physics that dominate the ISM or galaxy evolution, and then beginning to incorporate a lot of the physics that has been traditionally included in accretion disk simulations. So this plot over here is showing the mass resolution of the simulation as a function of distance from the black hole. So on large scale, this is just like a standard file simulation. Then we split the gas resolution elements getting closer to the black hole. And in the end, in the inner central parsec or so, we reach a mass resolution of 0.01 solar masses per year. So the code is solving the same equations continuously, MHD, radiation, thermochemistry, gravity identically. The only difference is how we model star formation, whether we model a lower resolution star particle that represents a stellar population with some assumed IMF, and then using feedback quantities from Starbus 99 as a stellar population synthesis model, and then a high enough resolution, we switch to a model where stars form one by one following the StarForge model by Mike Rudrick and collaborators, where the IMF is actually predicted. We are forming individual sync particles that keep accreting, there is protostellar feedback, and all sorts of detailed individual star evolution. So great, thank you. So in this plot that nobody can see, I was just trying to highlight the huge range of time scales involved in the problem. So from billion-year time scales on megaparsec scales all the way down to hours, basically, which makes simulations very slow. This plot here is showing the surface density as a function of distance to the black hole through different components. So dark matter dominating on large scales, stellar stars dominate from kiloparsec down to 0.1 parsec scales or something like that. And then the gas dominates at the center. So very surprising result of these simulations was basically seeing the end of star formation below 0.1 parsec. So here, the orange dot dash line is showing the star formation rate surface density. There is a very sharp drop at 0.1 parsec or so. What happens there is that the gas is so dense that it's becoming optically thin to its own cooling radiation. It really magnetically dominated the gas, and this is supporting against fragmentation. So there is basically the end of a star formation there on those scales. That means that gravitational torques are no longer nominal, and MHD torques are basically starting to dominate this strongly magnetized disk. The accretion rate versus time, which you can see in this plot, the black line is the inflow rate as a function of distance to the black hole. On milliparsec scales, we, for these very specific conditions, targeting bright quasar phase, we are indeed predicting quasar-like luminosities of up to a few tens of solar masses per year or in very short periods of time. Very turbulent disks, some very interesting M=1 modes that are induced from large scale asymmetries and then propagate inwards. And the origin of these very, very strong magnetic fields, which are basically fed from advection from magnetic flux from the ISM. So the magnetic fields come from cosmic seeds, basically tiny magnetic field seeds that they get amplified. Doug is looking at me like I'm super late. Bottom line, down to 1 parsec or so, very similar results as before. Stars dominate the torques. Below that, super interesting physics shutting down star formation. And then I'll not have time to cover any of the feedback stuff, but just an add that we have some very nice models for how resolution AGN wins. And Jonathan Mercedes Feliz will tell us about the possible positive versus negative impact of AGN using some of these simulations. And I'll stop here. Thank you very much.
Any questions?
It's a very beautiful talk, Daniel. I think in the beginning you showed one slide where the black holes start to grow fairly rapidly once the bulge mass kind of reaches 10 to the 9 solar masses or so.
Yep.
I was wondering if you can relate that phenomena to the small scale physics, you're actually simulating down to very small scales. And if you understand the connection between the galactic scale versus the black hole growth.
Yes, you mean here, right?
Yeah. Right.
Yeah, so in this case, this is dominated by stellar feedback, basically evacuating the nuclear gas reservoir. So at early times, the galaxies are very bursty, and each burst of star formation, you have an outflow driven by the combined like supernovae. And so this is and it's actually creating basically like a hole, like a central cavity. And so this is not allowing the galaxies growing, the black hole is not growing much, just very short periods of accretion that do not let the black hole really grow. At some point, the stellar potential in the galaxies has grown enough that the star formation switches from bursty to sort of more smoother star formation. And so stellar feedback is not as efficient, and then the winds, stellar feedback-driven winds can no longer escape the nuclear region. So that's sort of what we believe are the perfect conditions for black holes to start growing faster and catch up. And this is seen now in a range of simulations where we have many examples here in the audience.
Okay, thanks.
Sure.
Yeah, so in that sort of last plots or that you were showing from the where you were going all the way down, what was driving the outflows primarily? You had some outflow rates.
The outflows, yeah. So there is inflow and outflow basically everywhere. Here we are not I mean, in the same way that some things are torqued in, some things are torqued out. Here we are not modeling feedback. So for example, we are missing the inner winds or strong radiation from the inner accretion disk. We are missing that. So I should emphasize that.
There's stellar driven winds.
Oh, so yeah, that's right.
Some
So,
of the outflow is presumably from the stellar feedback, yes?
so on the larger scales, yes, that's right.
Not on, okay, not on the
I
smallest.
guess I was wondering why, because you said the torques are not important in the innermost regions, I thought.
So the gravitational torques.
Or they still are.
Very strong MHD torques. Yeah, so within 0.1 parsecs, there are no longer stars. So on those scales, that would be from the orange line to the left. So on those, let me show here.
Still have outflows there.
Yeah, I mean, that's right. Outflowing is super turbulent, so there is always a combination of both. The stellar field might be doing things, but from like above 0.1 parsec or so. Yeah.
Time for one more question. Someone has. Okay.
I'm just picking one for now, but how do you achieve such hyper resolution? I mean, what are your your refinement criteria? Do you just have incredible computing power? Like, how are you doing this? Yeah.
Yeah, thank you. So this is a Lagrangian code. So the gas is represented by particles that correspond to some amount of mass. And then the idea is we start with sort of a standard Thumin simulation. The resolution might be of order 10 to the 4 solar masses per particle, something like that. This one is even lower resolution on the larger scales. And then you just tell the code to split the gas elements as they get closer and closer to the black hole. So basically this radial profile in this plot shows sort of very strong refinement on the scales that are sort of interest. And the idea is to start refining so that we can capture the torques and the gas dynamics on the nuclear region. And then at some point we reach, the maximum level of refinement here is say 0.01 solar masses per particle. And then it gets very, very slow. So you need to be very patient. The scaling is horrible. Just the center is dominating all of the computing power. And so it's not practical to run this already. This runs for very short time, but I should say for many thousands of dynamical times on each relevant region. So these simulations run for very long on the sense of the dynamical times, but on cosmological time scales, this is just a tiny window. So we have to basically try and set up experiments like this targeting different conditions because we will never be able to do the full cosmological evolution.
Okay, let's thank Daniel again.
Thank you.
Next we have Trung Ha. This mouse is terrible.
Okay. Good morning, everyone. So before I start, I would like to say thank you to the organizer for giving me a chance to give a talk about my work. So my name is Trung Ha. I am a PhD student at the University of North Texas. And at the moment, I'm also a pre-doctoral fellow at the Center for Computational Astrophysics here at the Flatiron Institute. And today I'll tell you a little bit about my effort in modeling supermassive black hole feeding and feedback at the mesoscale. And I'm working primarily in collaboration with my PhD advisor, Yuan Li at UNT, and also Sean Ressler at the Canadian Institute for Theoretical Astrophysics. Okay. So first of all, when we think about the accretion model in black hole accretion, the first thing would come to mind would be the Bondi model. And very quickly, the Bondi model assumes a uniform density medium that is accreting onto a central point mass. However, through observation, we now know that this Bondi model does not quite be able to describe the environment that surrounds massive elliptical galaxy, for example, in the case of M87. So in the case of M87, if you look at the first plot here from Boselli et al. 2019, you can see that there is an extended filamentary structure from the H alpha gas, which is a cooler temperature medium. So instead, the model that we're suggesting is more of a turbulent two-phase model. So it's turbulent. For example, in Li et al. 2020, they were able to look at the velocity structure functions of the H alpha gas in the Virgo clusters, and they found structures of turbulence. Okay, so the picture that we're looking at right now is that multi-phase gas is accreted onto the supermassive black hole. Along the way, it's stirred up by the black hole feedback as well as other ISM turbulence driver. And especially in system like M87, the radial mode feedback plays an increasingly important role in maintaining the quiescent state of accretion. Okay, so to model this accretion down onto the mesoscale, first we start with a galaxy scale simulation. So this galaxy scale simulation is done in the Athena++ code, and we are using an initial condition that is similar to Gu et al. 2023. Thank you to Ming-Hao for sharing your work with us. Very briefly, the physics that we include in this simulation includes a static gravitational potential. So we have a dark matter halo, a stellar potential, as well as the potential coming from the supermassive black hole. We have an initial turbulence perturbation, which is just perturbation in the density at the start to seed turbulence for later. And we have radiative cooling as well as jet feedback. And this jet feedback, we try different values of a parameter called the jet kinetic fraction, which determines how much energy is input into the thermal versus the kinetic energy of the ejected gas. Okay, so here is an example of one of our simulation. So here we're looking at the entire simulation domain, which is a 128 kiloparsec box. And this is a slice spot in temperature. You can see that as the jet goes out, it drives a shock into the medium, and it facilitates turbulent mixing that will cool the gas as the cooler gas is accreted onto the supermassive black hole. Okay, we have to, in order to study the small scale accretion model, we have 10 levels of static mesh refinement. So that allows us to reach a maximum resolution of about 1 parsec at the center. And to a model, to keep track of the accretion, we have an inner boundary that is basically just a sink region of a radius of 5 parsecs. So that allows us to reach down to about 10,000 RGs. And before I move on further, I would like to show you some results from the galaxy scale simulation. First of all is the number density projection over time. And this is basically tracing the cooler gas that is formed throughout the simulation. So you can see there are extended filaments that is formed during the simulation, and then it's accreted and it forms a disk. And at 700 megayear, the video stops here so that we can zoom in to the central around 1 kiloparsecs. And we can look at how the disk evolved here. As you can see, kind of tell, there's a smaller inner disk and then a bigger outer disk. And as the inner disk is dissipated or accreted, the outer disk now move in and form the new inner disk. Okay, so a few plots on the time evolution of our simulation. First, we can see that so let me just go quickly through this. We have the plot for the accretion rate, the total mass within the Bondi radius, and the angular momentum normalized by the Keplerian angular momentum. Just the one thing I want to note is that if you look at the total angular momentum here, the blue plot, we can see that the peaks of the total angular momentum correspond to the troughs in the accretion rate and vice versa. And this is fairly intuitive because if the gas is orbiting around in a Keplerian disk, then there's not a lot of gas being accreted. And otherwise, when the gas is moving in radially inward, then there's accretion is higher. And also, if you look at LZ, which is the gray line here, you can see that it is oscillating back and forth between -1 and 1, which is telling us that at the Bondi radius, we are seeing a disk that is changing direction in orbit periodically. And you will see that in another video later. Another thing that we're interested in is the turbulence kinematics of the gas in this simulation. So here I have plotted the velocity structure function of the cold gas, which is in blue, and the hot gas, which is in orange. And curiously, or maybe it's a good thing, that if you look at the blue line and the blue line in the upper left panel, which is the observational velocity structure function of CO gas from ALMA of the Virgo cluster, that there is a kink in that structure function, a break in the slope that matches very well with the scale, the separation in the observation. Okay, and then because we want to study the accretion down onto as close to the center as possible, we also did the mesoscale simulation, which is done by adding more additional level of mesh refinement to the center of the galaxies, and also shrinking the inner boundaries at the same time. So here I have added 5 levels of additional mesh refinement, which allow us to reach down to about 0.03 parsecs. And that means we have an inner boundaries at 250 RGs. And for this simulation, we evolve it for 2 million years, and we turn off the jet feedback just to save some computational time. So in this time scale, the cold gas that would have been affected by the jet doesn't have enough time to fall down into the center yet. That's why we can turn off the jet. Okay, so let me show you a video of the now number density, but at 800 mega year, which is where we re-simulate and add additional refinement level. So here you might be able to see that there's an inner and outer disk. The inner disk is clearly orbiting in a counterclockwise direction, while the outer disk is orbiting in a clockwise direction. So that's just a visualization that I showed from the plot earlier. And we can also zoom in further because now we have additional levels of refinement in the center to about the center 10 parsecs of the galaxy, which is this. And you can see how the gas is spiraling inward into the center. And if you turn that face on, that this would be an example of a number density plot that we would see. Okay, and then I think this is the last thing before the final slide. We also plot some radial profile of the mesoscale simulation. We have temperature, number density, and angular momentum. And the only thing I want to note is that if you look at the number density radial profile, we're seeing a R-1 slope for the cold gas, while we see an R-2 slope for the cold gas. And my interpretation at the moment is that because the cold gas is mostly being accreted in a disk, while the hot gas is more volume filling and is accreting in a more spherically, that's why we see different slope in their number density. And yeah, so I just want to put up my summary slides, and a couple of things I want to note is our next step would be to include the magnetic field to study the role of magnetic support on the accretion flow, as well as expanding our simulation to a similar galaxy and galaxy cluster system to compare with observation. Thank you.
Any questions? Go first.
Yeah, hi. Thank you very much for your excellent talk. So I have a few questions. So I was wondering that in your case, your hot gas scaling is R⁻², right? Which is, I don't quite understand why, but in my case, I mean, it could be R⁻1, or maybe it's a strong mixing between hot gas and cold gas.
Okay.
And then that's related to the scaling of the mass accretion rate when you will do some zoom in. So the accretion rate might change, right? So I mean, the accretion rate might change according to your inner radius or sinc region. So can you talk more about that part? Yeah.
So I don't really have much that I can expand on. So my thinking right now is that the slope could be different for different, if we take different snapshots. Because I take the one snapshot to re-simulate where like a very stable disk has been formed. I wonder, I assume that when we re-simulate in the case where the disk is still, it's not really a disk where it's still chaotic, we could see a different slope that is formed. And also, just as a note, I'm doing a mass-weighted radial profile. I believe that in your paper you did volume weighted, because yeah, I also checked volume weighted radial profile, and I think my profile looks very similar to yours too.
Oh, thank you very much.
Hi, thanks for the talk. So you showed how the inner disk is rotating retrograde and the outer disk prograde, or whatever your frame of reference is. But before that, you showed that the inner disk gets accreted and then gets replenished by the outer disk. So does this pattern repeat?
Yes, I believe so. So when we only evolved this to 1 gig a year, but it seems to be the case where, yeah, so if you see the bright spot, they kind of shrink and disappear, and then another bright spot appears where the outer disk shrinks down to form the new inner disk, and then there's new gas being cooled from the outer part of the galaxies that now form the new disk.
Do you have any intuition why this change of direction happens?
Oh, I think that's more of just like because we have initial turbulence, like density turbulence perturbation. So when the gas is being formed from different part of the galaxy as they stream in, depending on where the location of the gas that is being formed, then it will have a different preferred direction.
Thanks.
One more question.
Nice talk. I was wondering, in like the video you showed earlier on, it looked like visually that the jet was processing, and I was wondering if the jet is actually processing or whether it's just interacting on small scales with ambient.
The jet is actually where we put a precession into the jet at I think 10 to 15 degrees, and the precession, the angle of precession change every 5 million years.
Right. Okay. Thank you.
I have a question.
Yeah.
Follow up to that, and I'm in control, so I can do it. So how do you like choose the initial jet direction in the first place? So you're processing it, but like, what's the initial?
It's a random initial.
Oh, it's just isotropic?
Yes.
Okay. Interesting. Let's thank Trung again. Next up, we have Amy Secunda.
Right. I have quit.
Hard angle. What's going on here? I've never actually used Keynote.
Well, hopefully it works.
Let's say, do I just click play for this one, I guess?
Yeah, you might need to click the first thing though, because it might play from this slide. So if you just go to the left and then scroll up, yeah.
Oh, here.
To the top, yeah. And
Right.
then, yeah, click
Oh, I
that.
see. Okay.
Yeah.
Thank you
Cool.
for doing my job for me. No. And you can just start. You have 12 minutes.
Awesome. Okay. All right. Good morning, everyone. My name is Amy Secunda. I'm a grad student at Princeton, and I'm going to be talking about simulating multi-waveband quasar light curves using radiation MHD simulations. So first, I'll just actually show you some observed AGN light curves. This is for the AGN Farrell 9, and these are light curves from SWIFT and LCO. And I'm showing you these light curves so that you kind of get an idea of what we're looking at with these multi-waveband simulations. So in the top panel, you can see there's an X-ray light curve that comes from SWIFT, and you can see that it varies over a wide range of timescales from days to months. And then in the middle and bottom, I'm showing you a light curve from Farrell 9 taken with SWIFT in the B band and the Z band. So these are UV and optical wave bands. And we think that these X-ray light curves come from the corona, the inner region surrounding the supermassive black hole, and that these UV optical wave bands come from the AGN disk, which according to its black body temperature will emit in the UV and optical as you move outwards in the disk. And so we can use these light curves to learn about AGN disk structure and AGN physics. And one of the main tools we use for this is called disk continuum reverberation mapping. And how this works is the corona emits these time varying X-rays, and some of them come straight towards us. But in some cases, the X-rays move outwards along an AGN disk. They get absorbed by the AGN disk, reprocessed, and then re-emitted based on the local black body temperature of the disk. So that if you look at these light curves, you'll see variability first in the X-ray, then in the UV, then in the optical. And that's because it takes the light crossing time for the light to move outwards in the disk. And so because we know the light crossing time, and because we can measure these lags, we can learn about the temperature, radial temperature profile of the disk, and also the radial extent of the disk. And so I can show you this again in the light curves. If you look, for example, in the peak, just short of 450 days in the X-ray light curve, and then you look in the B band, you can see that that peak occurs slightly later. And then if you look in the Z band, you can see it occurs even later. And again, we can use sophisticated methods to draw the lags out of this, and then learn about the characteristics of the AGN disk. But there are some problems. I mean, Shane talked earlier. For one, when we use this method to measure the radial extent of the disk, we predict a larger radial extent than our, Shakura-Sunyaev models predict. And whether that's a problem with our observations or a problem with our models, we don't really know yet. But also, if you just look at the light curves, you can already see that, this traditional picture that you have this X-ray light curve that essentially gets copied and pasted at later times in the UV and the optical isn't really the case, because you can see that the UV and optical light curves, the B band and Z band, are a lot smoother than the X-ray band. So some of this shorter timescale variability gets smoothed away. And then you can also see that if you look, there's a black line drawn through each of these light curves that shows kind of some of the long time scale variability of these light curves. And you can see in the Z and B band that there's kind of this shallow parabola shape. So there's some, low frequency, long time scale variability in these bands. But if you look in the X-ray band, it's pretty much a flat line. So it's not there. So, you're not really having this copy and paste. There's more going on than just the X-rays driving variability in the UV and optical. So we want to simulate this. So we do 3D shearing box simulations using Athena++. And so we drop a shearing box with a really narrow radial range into the UV emitting region of an AGN disk. And so these actually have, they're tall boxes because we want to make sure that we get the photosphere inside the box so that we can capture all of the flux that's leaving the box. But they're high enough resolution to resolve the magnetorotational instability, which is important because that can drive turbulence, which could produce variability in AGN light curves. And then we also, on that note, add some zero net flux magnetic fields, and we also ultimately add a vertical magnetic field in order to increase our Maxwell stress to get accretion rates that are similar to what's observed. So then importantly, we are using radiation in these simulations, and we initialize them in radiation hydrostatic equilibrium. I can probably just rush through this since Shane mentioned this. Again, using realistic opacities is important here. I can show on this figure from Jane et al. 2015, right? They show the opacity as a function of temperature for several densities. And you can see, again, around 10 to the 5 Kelvin, you have what's called the iron opacity bump that comes from, iron in the disk. And so this increase in opacity around these temperatures is important because somewhere between your midplane and your photosphere in your AGN disk in this UV emitting region, you're pretty much guaranteed to be 10 to the 5 Kelvin. And in our case, in our initial profile, it leads to a density inversion. And this density inversion also produces an entropy inversion, which drives convection in our simulations, which again is another source of fluctuations that can produce variability in the light curves emitted by the disk. So, okay, and then the final thing is that we are going to use 2 different frequency groups. So instead of just integrating our radiation frequencies from 0 to infinity, which is called like a gray radiative transfer, we're going to use 2 separate frequency groups. So first, we're going to use a low frequency group that's based on the local disk temperature. And so in this case, it's going to be UV. And then we're also going to use a high frequency group. So in this case, above 1 keV. And this is going to be the X-rays that we're going to inject into our simulation as if they're coming from the corona to be reprocessed by the disk. And in this case, we model this X-ray light curve. We make it time varying because that's how X-ray light curves are. We model it as a damped random walk, which is a pretty common way to model AGN light curves. So just to quickly review, right, we have the simulation. We run it with this low frequency radiation that's based on the temperature of the disk. We then inject a time varying X-ray light curve that's coming from the corona. And then we are going to measure the UV emission that's coming off of the disk that has been theoretically reprocessed from the injected X-ray light curve. So, okay, so I'll show you these light curves. So first, this is what we call the intrinsic UV light curve. So this comes from a run where we don't inject any X-rays at all. So this is just UV emission driven by fluctuations in the disk. Well, the variability is driven by fluctuations in the disk. And as you can see, it does vary quite a bit, even with no X-ray driver, on timescales of days to, even 100 days. So a wide range of variability. Next, we inject this X-ray light curve. And I'm actually going to show you, if I have time, 2 different simulations that are identical, except for I inject 2 very different kinds of X-ray light curves. So here, we model it as a damp random walk with a damping timescale of 0.1 days. So it has a lot of high frequency variability, but not a lot of this low frequency variability. We want to see how that is going to affect the intrinsic UV light curve. And so this is what we get. This is our reprocessed X-ray light curve. And I'll do it like this so that we can compare. So if first you look in the top panel, I'm showing the UV light curve with and without the injected X-rays. And you can see that they actually have a lot of similarities. We calculate the Pearson R coefficient and find that they're not strongly correlated, but they are correlated. So the correlation coefficient is 0.54. But if we look in the bottom panel, right now we're comparing the UV light curve and the injected X-ray light curve. And you can see that they're not very well correlated. And when we try and find correlation between them, we don't find a significant correlation. And I can also downsample that bottom panel just so that it's easier to see some of the variability in the X-ray light curve. And, there are points where the 2 match up. They are similar at points, right? The UV, intrinsic UV and this reprocessed UV light curve, don't perfectly match up. So it's clear the X-rays are having some impact. We can actually zoom in. If I'm just showing you 10 days worth of the light curve, now we can actually look at the highest frequency variability. And you can see, first of all, that again, the UV has high frequency variability, not a lot, but it does have some, even if I'm not injecting the X-rays. But the X-rays do have some impact. You can see, for example, here, where this X-ray variability seems to change what the what the short time scale variability would be of this light curve. So it has some impact, but it doesn't actually seem to give more high frequency variability in the UV light curve, right? The amount of high frequency variability seems to be the same. And so, we can look at the power spectral densities of the X-ray, the intrinsic UV, and the reprocessed UV light curves. And you can see that the 2 UV light curve, the 2 UV PSDs are nearly identical. Whereas the X-ray light curve has so much more power at these high frequencies, but it doesn't seem like any of that is coming into the UV light curves. And so, we think that that's actually related to what we see here. So not only can we measure the UV flux that leaves the box, but we can measure the X-ray flux that leaves the box, right? And we see that the emitted X-rays have a lot less power at these high frequencies as well. And that's because these AGN disks actually have incredibly low absorption opacities for X-rays. So here I'm showing the absorption optical depth in red for the X-rays, and then in blue and purple for the 2 UV simulations. And you can just see that there's almost no absorption opacity, which means all of these X-rays pretty much are being scattered. And because of that, it seems like these highest frequency variability is being smoothed. And so I can also show you, right, here I'm showing the horizontally averaged vertical profiles for the temperature as a function of time. And on one side of the gray line, I guess to the right, well, to the left from your angle, is the run where we don't inject X-rays. And to the right is the run where we do. So and the white line shows actually the location of the photosphere. So you can see that there is significant heating, especially in the photosphere when we inject the X-rays, and it even goes down within the photosphere. And so what we think this picture is you have X-rays, they scatter and give a momentum transfer to the gas, and that eventually thermalizes. And that's what produces, again, some changes in the light curve and this heating. And we can actually see that for a different X-ray light curve. So here, the blue is again the intrinsic variability, the green is the reprocessed UV, and now the orange is a different injected X-ray light curve. So I'm showing the PSD so you can see that it has a very different shape. Now we model the damping timescale as 10 days instead of 0.1 days. So it now has a lot more low frequency variability. And that actually makes all the difference. So now if I show you the light curves, again, we find a weak correlation between the two different UV, but now we also find a significant weak correlation between the X-ray and the UV. And that's because it seems like these lower frequency variations in the X-ray light curve can drive variability in the UV. Because they don't get as smoothed by the scattering. So there is some reprocessing. It's interesting, these results kind of agree with recent reverberation mapping campaigns done using Swift that find that often the X-ray and the UV and optical are not super well correlated with each other. They have, again, this kind of 0.52 correlation. And so all of this just suggests that this high frequency, this high energy UV is maybe not the only driver or even the main driver of variability in UV light curves. So we have to maybe rethink our picture of reverberation mapping. So I'm out of time. I'll just leave my conclusions up here, but thank you so much.
Are there any questions? Amy?
Yeah, so for the when people actually model the X-rays with the damped random walk, what damping time scale do they typically fit? So how does that compare to the two limits you assumed?
Yeah, so I mean, one thing that we struggled with figuring out is that, it's hard because, the time step of our simulations is so short. And, we don't have much sub-day observations of X-rays from AGN themselves. But I think actually, from talking to some observers, I actually think this PSD, so a damping timescale more on the order of 10 days is more common. On the other hand, when we think about what sets the damping timescale, people think it's the thermal timescale. So we think about what the thermal timescale might be in the region emitting X-rays. That's kind of where we get the 0.1 days from, right? It should be a shorter timescale. So, I don't know if we really know, but I definitely, when I show this plot to observers, they're much more comfortable with this PSD. So I'll say that. We were kind of interested in this, kind of the first PSD I showed because, when we looked at this, we didn't see any additional high frequency. And so we were curious that if we turned up the amount of high frequency variability in the X-rays, if it would drive more high frequency variability in the UV, and it was still no, so.
Okay, one more question.
Hi there, Antonio here. I wanted to ask if you go through your simulation, try to calculate black hole masses using this method, do you get black hole masses similar to the ones from Swift or all these other observational data?
So so I should say what I'm looking at here is discontinuum reverberation mapping, and most of the time to measure black hole masses, it's actually a different type of reverberation mapping where they measure it related to the broadline region. And so, I think this might have some applicability to that. I mean, there's definitely some work being done trying to make sure that when you do discontinuum reverberation mapping, you're not, getting contamination from broadline region observations. So, I think it could have an impact on that. But as far as I know, I don't actually think you can use specifically discontinuum reverberation mapping. You can't use the continuum as much to measure the black hole mass.
Thank you.
Thank Amy again. Sorry. Now we have Minghao Guo. So much better. Yeah. Nice. Yeah. There you go. Oh, just start your talk.
Hi. So hi everyone, I'm Minghao Guo. So I'm a current third-year grad student at Princeton, working with Professor Jim Stone and Alex Coulter on this kind of multi-scale modeling of black hole accretion. So in this talk, I'll talk some kind of work we are currently doing about toward horizon scale accretion onto supermassive black holes in some elliptical galaxies, which is a big topic. So it's pretty, there's lots of physics happening over here from the black hole scale, which could be like the Schwarzschild radii, which could be like maybe 10⁻⁹ are very viral, all the way out to the viral radius of the cluster, which could be 9 orders of magnitude larger. So which is a sizable dynamical range. So it's a well-known, long-standing, hard-solving problem. And there's also a variety of physical processes, including some radiative cooling, heating, turbulence, magnetic fields, and jet, and lots of physics here. So here, what I'm focusing on is this part, which is basically from roughly the galaxy scale, which could be like 30 or 40 kiloparsec, all the way down to the horizon scale. We are trying to link this kind of slightly larger scale turbulence and some physics there, and to see that what would be the final accretion rate going to the horizon scale. So specifically in the case of the galaxy M87, which is pretty interesting because we have the photo of this black hole. So here we, from larger scale, can run some galaxy simulation, and it's down to small scale, we can run geometric simulations. But in the between, here we have to use a series of nested mesh, hydro, and MHD simulations to really trace the accretion flow from the galaxy scale down to horizon scale. And in this case, specifically, what's important are, one is the boundary scale, which is roughly 100 parsec, with accretion rate of roughly 0.1 solar mass per year. And another important thing is the cooling of the hot gas, which could dominate the accretion rate when the cooling time is roughly short compared with the free fall time, and can increase the accretion rate by a factor of like 10 or 100 or even more. So we have to consider this. But still, for this case, typically it's not that high in the ratio equation. It could be slightly higher. And then the way we are doing is using this kind of zoom-in simulations from largest scale, which is, as Changha has already talked about, which could be like from 30 kiloparsec or even 100 kiloparsec down to some parsec scale. And when we run this for a sufficient long time, which could be 100 or 1,000 local dynamical time scale, and then we can use this as the initial condition and boundary condition for some smaller scale simulations with, of course, some cooling and heating mechanism included. And we can keep doing this until we reach the event horizon. So here specifically, we can run from 10 levels to 15, 20, and even 25 levels, which finally we can resolve the horizon with a resolution of roughly 0.1 or 0.01 RG. And we are using Cartesian coordinates using identikit to avoid some discontinuities and for performance portability, which can really run some large scale simulations, because if we really want to resolve the cold gas, which could be very thin due to their relatively low temperature and the less pressure support. So here to start with, I want to discuss a toy model, which is basically a hot equation, but with some turbulence, which is pretty like boundary, but it significantly deviates from boundary equation because the mass scaling and the equation rate scaling is significantly different from a boundary equation. The equation rate totally is basically turbulent with both a strong inflow and outflow. And then finally back a little bit from the mic here, yeah. And then finally you could see that this is much better. So in this case, you could see that with a different inner radius, the equation rate would be slightly different and following a scaling of roughly square root of r. And then you could see that finally when we trace this to the equation rate, when we trace this simulation to the even the horizon, the equation rate would be like 2 orders of magnitude lower than the boundary rate. So this is a significant difference from a boundary equation. And the most important thing compared with boundary equation is then the scaling of density, which is also different, which is basically r to -1 instead of to the 3/2. Then there is why this is such a scaling. So this is which I believe Wenrui Xu would talk a little bit this afternoon about the details of this physics behind this. But basically, it's which we can call that simple convective equation flow, which is driven locally by convection processes, and it depends on the adiabatic index. But for the adiabatic index we are using here for this ionized gas, which is basically 5/3. The scaling is still roughly r to the square root of r. So the mass equation rate would be kind of similar to here the case. But of course, maybe we are doing some different adiabatic index and maybe face some kind of cooling to be slightly different. And then when we are going to our Photoshop suite of the simulations, which will include cooling, then we would form we would naturally form a two-phase gas. Then the most important stuff is that we would find that there are 2 stages. One is the so-called chaotic stage, and another is a disky stage. And they can occur intermittently in the simulations. So here, there is one simulation. I'm not sure how to. So beginning, we can form a small torus, and sometimes it's chaotic, and sometimes when the torus form and it's disappear accreted, and then we'll form a new torus again. And when we do zoom in, you could see that the torus is actually slightly tilted on different radii. Basically, the angular momentum directions of the disk can be actually significantly different on different scales. And sometimes we would find some kind of 2 tori structure or even multiple tori structures. And then there are 2 simulations. Left is with more turbulence, and the right is less turbulence. You could say that with more turbulence, that we would tend to form more torus at different radii, and the torus size could be significantly different. And on the right, when we have some kind of relatively similar angular momentum, we would form a large torus or large disk, which can sustain for a sufficient long time, which could be like 100 million years or so. Then while doing zoom in, you could see is that the orientation of disk differs on significantly different on different scales. With a warm disk, and streamlines are laminar on small scales, basically. But the equation mostly is from the polar region. Here, even though we have lots of cold gas, but when we trace the equation flow down to small radii, typically it's still dominated by the hot gas, because we are doing a hydro simulation without any explicit viscosity, so there's no enough mechanism to drive the angular momentum transfer. And hot gas both accretes to the small radii and condensed onto the surface of cold disk. This is for the disk equation, which occupy maybe 90% of the equation of the time of the duration. But for the chaotic equation, which typically corresponds to a higher equation rate, the equation, the streamlines are more chaotic but still we would find that there's a small disk within the parsec scale. Because you always have some you won't have a 0 angular momentum. You always have some small angular momentum, and they are typically much larger than your boundary the gravitational radius. So typically we would have a small radii, a small torus. Then the angular average, the snapshot of the disk equation clearly shows the equation flow structures. So most equation is still dominated by the hot gas from the polar region, and the condensation of the hot gas to the cold disk will lead to the decrease of the equation rate, which we are showing later. Here is a time evolution of the equation rate. Basically, you can see that the equation rate would evolve between the cooling limit and the adiabatic limit, with a typical equation rate of roughly like 1 solar mass per year with angular momentum change frequently. You could see that the total angular momentum is of course always capillary, nearly always capillary, but the direction of the disk changes significantly with the cold mass also can change significantly from like 1 million solar mass to 100 million solar mass. Then when we trace the equation flow dot to the down to small radii, even though we have a more complex structure, still the equation rate is scaling in with the radii following a square root of r. And the higher m dot is that we still, but for chaotic case, maybe that's different because we always have a higher m dot. But when we form a disk, then finally it would still follow this kind of scaling. Yeah, 2 minutes. Okay, maybe lots of. But basically, what we are finding is that here then the equation rate, even though the equation flow structure is significantly different from the adiabatic case, but still the equation rate is scaling is quite similar to the square root of r. But though the mechanism behind that is possibly not due to turbulence, but due to the interaction between cold gas and cold gas, in which the hot gas can condense down to the surface of cold disk, so that the amount of hot gas being accreted is still decreasing with a smaller radii. And the emission rated temperature profile could be flat, which might explain the observations where you will not find a significant temperature jump to high temperature within boundary radius, but because due to the strong interaction between the hot gas and cold gas. And the hot gas is always slightly unbound and subcapillary. So then put all this together, we still find this kind of beautiful scaling of square root of r for a variety of situations, so that it can sell, and the final equation would be surprisingly similar to the event horizon observations. And the contribution of hot gas and cold gas can vary on different spatial and time scales. And finally, we are running some MHD and GRMHD simulations, but in this case, the disk properties is significantly different. So the gas is highly magnetized. So we have some outflows. The disk is much puffier, but and still surprisingly, the equation rate is still scaling with radius following a roughly square root of r, even though the disk structure is significantly different. And going to a small radii, I would find that there's a misaligned disk. The disk direction has no correlation with the spin of black hole. So, but still we can drive a jet, which can extend to a larger scale. But the jet direction might be strongly influenced by the direction of the gas, or the cold gas, or the hot gas. So stay tuned. We will have more results coming soon later. Thank you very much. Thank you.
Hi, thanks for the nice talk. I was just wondering, when you do GRMHD simulations, do you treat that as the next nested simulation from your MHD simulations, or how are you actually doing?
Yeah, so basically from MHD to GRMHD, we are doing some, but I think now the issue is that maybe there are some values different from in the inner region. So we are basically doing the simulations going to larger radii. We basically transfer all the variables to the primitive variables in the GRMHD variables. You're doing some conversion. Then I think by evolving the GRMHD for a longer time, we can self-consider get equation flow structures. Yeah.
Hi, I really enjoyed your talk. I have 2 questions.
Yes.
So one of them is, I might have missed, but you showed that the m dot scales as the square root of r.
Yeah, basically.
For both the case where you have cooling, so you have phase mixing between the hot and the cold, and the case where you have no cooling, the adiabatic case.
Yeah, here is summarizing all the case. So here there's some adiabatic cases following the square root of r perfectly. For the case with cooling, and we have both cold gas and cold gas present, but still the scaling is pretty similar, but maybe the normalization would be slightly different. And the outlier is the chaotic equation, where you could see that on larger scale, the equation can be significantly higher, and the scaling is not that similar to the.
Right. So my question is, so the physics is so different between the 2 scenarios. Why is the scaling the same?
Yes, so that's a very interesting question, and I'm not quite sure why, but maybe it seems like maybe there are some physics behind which we do not quite understand. But maybe they are due to some different physics because of gravity flow structure is very different. But maybe there are something more universal. But at least this kind of scaling is pretty robust, even in the presence of magnetic field. So maybe this scaling may be very useful in the future. We are doing some subgrid model for the black hole accretion.
Thanks. I'll ask the other question later.
Yeah.
Are there any other questions?
Thank you. I loved your talk. You showed that the angular momentum has some really variable oscillations. Does the change in angular momentum correspond with any phenomenon in your simulation?
I mean, yeah, the change in angular momentum basically corresponds to some infalling filaments of cold gas, which has no correlation with the disk angular momentum of the previous disk, so it can change angular momentum significantly. So that's the basic phenomenon, which is also pretty similar to what Chang Ha found. Yeah.
Thank you. Are there any other questions? I have a question. Oh, is there one over there? Is someone raising? Oh, okay, sorry. Now my question's not good.
Oh. Mine is probably not great either. Here you go. Mine's
standard question. So for the magnetic fields, how do you initialize that, and have you varied that? And if you did, does it matter for the results you get?
Now for magnetic field, we are initialized using a vector potential, so that we keep a constant plasma beta. We try maybe 10 to the 4 and 10 to the, basically it's an entangled random magnetic field. We only drive it on the largest scale, could be like 10 kiloparsec or few kiloparsec. And we try plasma beta of 10 to the 4 or 10 to the 2. But actually, there are something interesting is happening. So when we are going to some lower plasma beta, the disk is not, but I'm not sure whether that's robust, but it's because it's still ongoing. But when the plasma beta is lower, actually there is not such a disk. There's lots of cold filaments directly falling down to the central region, possibly due to the strong, because they are strong magnetized. But it still remains to be investigated. And maybe in that case, the accretion flow structure might be different, but I haven't shown that here.
Nice. Let's thank Ming Hao again and all of the speakers this morning.